Hey everyone, welcome back to the Explainer. So, I was digging through some recent AI research the other day, and I stumbled across a paper that honestly completely blew my mind. It's called Risk is Not the Target, and it fundamentally shifts how we need to evaluate AI risk systems out there in the real world. If you're the kind of person who loves understanding exactly how complex systems tick, well, we are going to have a lot of fun with this one today. We're diving into exactly why a model that looks absolutely perfect on paper might actually cause a real-world disaster, and more importantly, how a totally new evaluation framework is fixing that. Okay, so here's our roadmap for today. We'll start with the ML binary trap, then look at evaluating operational coherence, move on to benchmarking AI and experts, and finally, wrap up with fixing risk assessment pipelines. Let's kick things off with part one, the ML binary trap, and why statistical accuracy just isn't enough. Now, this brings up a massive disconnect. I want you to just think about this for a second. Why do highly accurate AI models, like models that score literally perfectly on all our standard lab tests, why do they routinely fail when we actually deploy them in the real world? Imagine a wildfire prediction system, right? The researchers train it, it predicts fires with flying colors in the lab, but then the fire department actually tries to use it on the ground, and it's completely useless. Why does that happen?
Well, standard ML metrics, things like F1 score or intersection over union, they treat risk as a discrete binary event. Like, will there be a fire? Yes or no? Did it cross a specific threshold boundary? Yes or no? But the thing is, operational reality doesn't work on a simple binary toggle switch. Fire departments have to operate on a continuous gradient dial. They have to manage continuous risk signals to figure out, okay, exactly how many trucks do we send, how many crews do we need on standby, and where do we deploy those resources at any given hour.
So, when a model is optimized purely for statistical classification accuracy, it creates this massive structural mismatch with actual human workloads. Because the fundamental rule of real-world utility is this: when a risk score rises, the operational load should rise proportionally. If an AI gives you, high classification accuracy, but it produces erratic risk scores that just jump all over the place without aligning to the actual workload, it's essentially useless. Risk managers need smooth gradient signals to allocate their crews, not just a binary flag. Which brings us to Section 2, evaluating operational coherence and a new metric for AI risk. So if those standard metrics are misleading us, what's the actual solution here? Well, the authors of this paper introduce a completely new evaluation framework, and they call it monotonic evaluation. Basically, this measures whether increases in a predicted risk score consistently correspond to increases in observed operational load. And notice how this completely shifts the target. The goal here is no longer just accurate fire prediction. The goal is ordinal coherence across the entire risk scale. It checks whether the risk scale actually meaningfully explains operational dynamics across the full range of predicted values, rather than just, hitting a discrete boundary. To make this a bit more concrete, this monotonic framework tracks three very specific real-world metrics. Number one, the number of fires. Number two, intervention time. And number three, deployed resources. This framework doesn't just hand the AI a high score because it guessed a fire would happen, right? Instead, it rewards the AI if an increase in its risk score reliably correlates with longer intervention times and more deployed resources on the ground. It literally forces the AI to align with the actual physical load that's being placed on the fire department. All right, moving on to Section 3, benchmarking AI and experts, looking specifically at the Alps Maritimes case study. Okay, so the researchers actually put this to the test in the real world. They benchmarked these ideas in the French Alps Maritimes department. And get this, the results are totally counterintuitive. They tested three structurally different approaches. First up, the DFE index, which is an expert-based heuristic system. Second, GRU models, predictive AI models using gated recurrent units. And third, FARS, which is a hybrid multi-agent system that combines predictive AI with LMM-based reasoning. Now, you'd probably expect the advanced hybrid LLM to win, right? Nope, wrong. The basic expert DFE index, even though it exhibited poor classification metrics, demonstrated the absolute best, most balanced monotonic behavior. Its risk levels distributed consistently with the operational load. The GRU AI models, they achieved strong local monotonicity, but they failed broadly. They ended up compressing or spiking predictions, which totally breaks that continuous scaling that fire departments desperately need for resource planning. And then we have the FARS hybrid model. Why did the multi-agent LLM fail? Well, because LLMs do not fix structural flaws. Period. They inherit the distributional boundaries of their inputs. The LLM reasoning layer couldn't just magically correct the distributional flaws of the underlying predictive AI. Actually, it was worse. The hybrid system actually amplified those existing signal boundaries instead of smoothing them out. So, if your base predictive model cannot properly distribute risk levels, layering an LLM agent on top is really just going to surface and amplify those exact same limitations. There's this one quote from the paper that just perfectly captures this whole shift. They wrote, "A good risk model does not predict fires accurately. It produces an ordinal scale that meaningfully explains operational dynamics." I mean, wow. That completely redefines what success looks like in applied machine learning. We absolutely have to stop optimizing for statistical accuracy at the expense of practical utility.
That leads us to our final section, Part 4, Fixing Risk Assessment Pipelines and some actionable takeaways for developers. For those of you out there actually building and managing these systems, how do we turn all this theory into practice? It's surprisingly straightforward if you adopt the right mindset early on in development. Step 1. Drop F1 score and IOU in continuous risk domains. Honestly, they just reward boundary fitting, not operational scaling. Step 2. Implement continuous scaling audits. You really need to validate that your output distribution actually aligns with downstream load metrics. Like, check if higher risk scores consistently trigger higher intervention times. You can do this by integrating monotonicity constraints into your loss functions or by using things like isotonic calibration and monotonic regression before deployment. And step 3, audit your upstream signals before you even think about adding LLMs. Multi-agent orchestration is absolutely not going to save a structurally flawed base model.
Now, if you want to dive into the math and actually implement this yourself, the authors have made it super accessible. The full monotonic evaluation framework code is available on GitHub, and all the extensive methodology, the specific Alps Maritimes dataset specifications, and the statistical validations are all up there on Argiv. You can find literally all the regional parameters and monotonicity thresholds they use to replicate this exact pipeline.
To wrap things up, I want to leave you with this final kind of provocative thought to chew on before your next deployment. If your model compresses risk levels or produces erratic jumps just to achieve a high classification accuracy, how will your operations actually survive in production? Because when those fire alarms start ringing, the gradient dial matters a whole lot more than the binary toggle. Thank you so much for joining me today to unpack this fascinating paper. Keep learning, keep building, and I'll see you in the next explainer.